Sure. Hello, everyone. Welcome to the online seminar on the mathematical foundations of data science. Thank you all for joining today. Our seminar is generously sponsored by 2 Sigma. It's my great honor to introduce our prestigious speaker, Professor David Morton. Professor Morton is a David A. and Karen Richard Sachs Professor and Department Chair in the Department of Industrial Engineering and Management Sciences at Northwestern University. He has made great contributions to stochastic optimization, and his research interests include stochastic optimization for decision-making under uncertainty. He worked as a Fulbright scholar at Charles University in Prague, and he was a finalist for the Euro Excellence in Practice Paper Prize, and he is also an Informs Fellow. He served as the Informs Optimization Chair, and he was a recipient of the NSF PCASE Award. The title of his talk today is Distributionally Robust Two- and Multi-Stage Stochastic Programming. Without further ado, please join me in welcoming him.
So thanks very much, Sharon. Thanks, Ethan and Sharon. Let me see if I can share my screen. Okay, so let me know if that's okay. Great, thanks. So really appreciate the chance to present, and also appreciate the great seminar series that you all have put together. So this is going to be joint work with Daniel Duque, who was a PhD student that I worked with here at Northwestern, is now at the OR group at Google. And also this first part of the talk will be joint with Sanjay Mehrotra, my colleague here. So the context here for starters is a two-stage stochastic program. And so in this setting, we've got some decision vector X that could be first stage. We could have C, which is a random vector. And in this nominal formulation, it's got a known distribution. And in the sort of simple prototype setup, that value function V is a linear program. And the way I wrote it here is that uncertainty is only appearing in the right-hand side. So you can think of it as a random demand, for instance. So like just a couple common examples. One is like an inventory management. So if it's a two-stage model, you kind of a strategic decision in terms of sizing a system with initial inventory. And then C could be random demand, and then you could pay holding or out of stock costs. So that could either be strategic, or it could be kind of a multi-stage operational model where you're continually reordering inventory. And another common example that shows up with some frequency, and at least in the stochastic programming setting, is hydroelectric power, where you have random inflows that show up in that right-hand side through the C vector. And then you've got a network of reservoirs, and you've got operations decisions in terms of how much to generate and how much to hold in inventory. And you're trying to minimize the complementary thermal generation cost. So we're going to be talking about DRO, so distributionally robust optimization, but sort of a dual formulation involves risk aversion. And so here you could take a risk averse function rho of that cost or value function. So it could be like a disutility function for a CVAR, or an entropic risk measure, or some other coherent or convex risk measure. So now in the context of DRO, we kind of get this game theoretic setup where you're minimizing with respect to X, but then it's a game against nature, where nature gets to choose the probability distribution P from some class cal P in this minimax form. So the setup is identical in terms of the decision X. It's identical in terms of the random vector C and this value function. But now, instead of taking a pre-specified distribution, nature gets to pick a worst case distribution from some class that we are going to specify. So why would you want to do this? And it's probably important to emphasize that we really don't think nature kind of despite the last year plus. We really don't think nature is out to get us. We don't think that we're going to make a decision and then nature is going to say, oh, wow, you made that decision, so I'm going to pick a worst case distribution knowing what you did. So rather, I think the motivation could be that we're uncomfortable in terms of fitting a parametric distribution to data and having the errors that show up in that fitting process be completely ignorant of the actual decisions that we're going to be making. So one way to try to kind of integrate the decision-making process and sort of minimization with respect to a loss function is DRO. Another way is that we're having a hard time kind of picking up a risk, a disutility function. And we see this as an attractive way to model risk. Or the third reason could just be regularization, that you know, there's no risk aversion or anything going on. We're just worried about overfitting our specific decisions to the data that we've observed. Okay, so we need to talk about this ambiguity set, this CalP. So CN, this is going to be a data-driven approach, is that we have data that we believe is representative of what we'll see when we in the future when we make this decision. And so whenever I have like a superscript n on C, it's going to refer to this this finite set of data. And then we could have an empirical distribution, so you can just think of this as 1 over n for each of the n realizations. And then we'll have marginal distributions for reasons that'll become clear in just a second in terms of the Wasserstein setup. So we'll consider two different kinds of sets. One will be, hey, we've only got these n scenarios, and these are our points of support. And nature can change the probability mass that assigns to those existing points of support. Or if there's not a superscript n on the support C, then we're going to allow nature to change the points of support, both change the probability mass associated with the points of support and change the points of support themselves. And we'll come back in time to this epsilon. How do we pick this radius? So there are lots of different distance measures, but one that has been seeing some use is the Wasserstein distance. And so in this setting, you can think of a transportation problem. On the left-hand side, we have sort of the origins, and they each have mass like 1 by n. And then on the right-hand side, just for the moment, let's think of that distribution as also being fixed. And so that's some other distribution given by p. And then the z here that's being minimized is actually a joint distribution across the Cartesian product of those sets of realizations. And it's got marginals that are specified by the Q and the P. All right, this is just sort of one version of Wasserstein. Right, we can have a P norm here that measures the distance between the 2 points of support. But there's other things we can do in terms of, you know, for example, taking the square and then the square root of the whole thing. But for simplicity, I'll largely run with this. And so this is what happens when we define it on Cn, that the existing points of support are fixed. Okay, so we're trying to get to being able to solve this minimax problem. And so using an extended variable formulation here, we can basically say, hey, nature gets to choose from the set P here. And then we use this extended variable formulation with the z's in order to say, hey, what distributions are going to be allowable? And of course, if you want to embed additional constraints in this set, for example, moment constraints, then that would be doable. Okay, so heading towards solving this this minimax problem, we min over x, we max over p, and p is in this cal p set. Okay, so let's fix the outer, right? There's a minimax, right? So let's fix the outer x and just focus on nature's inner problem. So in what I said before, both Q and P were fixed when we defined the Wasserstein distance, but now nature is getting to simultaneously optimize over P and then this auxiliary variable Z, and Q is a given. So it's optimizing over P to maximize this expectation, but it can't just put all the mass on the single worst case scenario, because the Z's that it pick have to be within a radius epsilon of the given distribution Q. So this is kind of nature's problem when the V for the moment is just data. Oh, and then by the way, right, if the way I've written things here, there's just these existing points of support. And sigma is the index for the origin, omega is the index for the destination, and suppose the destination were really a continuum. So in that case, what you basically see is, even though P is a decision variable, we could just substitute out for P here, and then we would just have n plus 1 structural constraints. So we can basically see that from what we know about linear programming, that even if nature is allowed to put probability mass over a continuum of possible points, it's only going to choose n plus 1, at most n plus 1 points to receive probability a positive mass P. Okay, so let's take the dual, right? This is just a linear program. So we're gonna use dual variables gamma on this radius constraint, nu, and then beta is, as I've already hinted, is something that could just be substituted out. And so when you take that dual, you end up with a minimization problem. And we want to do this because instead of having a min-max, now we can have an integrated minimization problem for both our decision X and nature's decision. And so it's really pretty simple to see what's going on here. Is Q is the existing probability distribution. And let's think about these extreme cases when epsilon equals 0 or epsilon grows large to plus infinity. Then if epsilon is equal to 0, then gamma can be as large, gamma, which is non-negative, can be as large as it wants. And when gamma is as large as it wants, it makes this constraint vacuous. Well, it makes it vacuous except for when sigma is equal to omega and that distance is 0. And so then in that case, we have this new sigma is just going to be equal to the value function evaluated at C sigma. And so in that case, this just reduces to the nominal problem, the existing expectation, because the Wasserstein radius is 0. On the other hand, in the limit as epsilon grows large and that Wasserstein distance is arbitrarily large, then we pay a huge penalty for the gamma. So gamma is going to be driven to 0. And then in this case, we can see that we're going to have a new sigma has to be bigger than this for all values of omega. And so that means that new sigma is just going to take on the single largest value function. And that's just going to be the worst case scenario is what pops out. But of course, we're interested in values of sigma that, or values of epsilon that lie in between these extremes. Okay, so now there's kind of a fork in the road here. And we're gonna briefly follow one fork, which is to say, hey, I really do have this two-stage stochastic LP. And I'm willing to say, I'm only interested in these n points of support, and that's the end of the story. So how do we solve that? So we'll quickly address that, and then we'll go back to the kind of more interesting story. Okay, so if we have the two-stage stochastic LP, then the value function is given by this LP. So I'm just going to plug in for that V here. So I plugged in for that V, that's the this second stage cost. I just plugged in for the dynamics of the first stage decision X and the second stage decision Y. For the moment, we're still just looking at nature's inner problem. But now we opened it up to bring in the outer minimization over X. So now we're minimizing over X and Y simultaneously. There's the auxiliary dual variable gamma, which was the scalar variable on the radius constraint. And then there were the auxiliary dual variables nu that we saw before, which are basically saying, hey, what's the value function under each realization sigma? So this is it. If the storyline is you've got this two-stage stochastic LP, you have these fixed points of support, nature only gets to mess with the probability mass on those fixed points of support, then you can see that, hey, what we end up with is a large-scale linear program. And we paid a price here in the sense that it appears to be quadratically larger because there's n-squared constraints that sit here. And it's true that if you just try to solve this LP exactly or directly, then that's what happens. However, if you run like a Bender's or Kelly cutting plane algorithm, then it's not quite that bad, right? You can do the separation problem more efficiently. And if you wanted to have first stage integer restrictions on the x, that's perfectly fine in this setting. All right, so that's kind of the end of the line where the story is we just have these fixed points of support and nature can change the probability mass. So now let's go back and ask the question, hey, suppose this Cn, suppose we change it to potentially a continuum of not over an index set, but over all realizations of Xi instead of just omega from the n pre-specified points of support. So now we're going to have this continuum, and how do we deal with that? Right, so for the moment, we're again in just nature's inner minimization problem. The outer x has been fixed, and so this value function here is just data. Well, it's at least data given x and given Xi. All right, so I'm just going to move this distance measure to the other side, and then say, okay, we have sort of infinitely many constraints here in general because we're writing this down for all Xi. So let's pull that inside and just take the max over all Xi that sits here. And so you can kind of see what's happening is that, right, the nu is our proxy for what the value function is under sigma, that plus this additional term out front. And so we're going to have the value function. Nature can make the cost function worse, for example, by increasing the value of the demand. But nature has to pay a penalty as it moves Xi away from the nominal point of support that's indexed by sigma. All right. Well, I don't really need that new variable. I can just plug into the objective function here, and again have this this overall setting where the only variable that has now kind of remained from the dualization is the scalar variable gamma. Well, that plus the fact that nature is changing the point of support inside here. Okay, so let's kind of look at the same question. We haven't done anything with this specific value function yet, but suppose we're in this LP setting where there's just demand in the right-hand side. And suppose that we take the dual here because nature is maximizing over Xi, and so it's going to be convenient to simultaneously maximize over the dual variable for the second stage LP. All right. So this is the setup we have, and now we're going to say we need to talk about kind of the structure that that nature has access to in terms of this support Xi. So there's going to be another sort of fork in the road, three-way fork, where it could be, hey, just the support is all of Rm, right? That I have, you know, the distribution's not pre-specified, of course, but like if it were multivariate normal, then I could have all of Rm. You know, if I had a log normal distribution, at least nominally, I would be in the positive orthant, or I could have some other convex cone. And so we're going to look at that case first, where we have this unbounded support. And then we're going to look at box constraints on Xi. And then we're going to change the this norm here for how we penalize how costly it is for nature to move the point of a support. Okay, so let's just assume that Xi is all of our M and try to understand how can we reformulate this problem for computational tractability in this case. So here are two simple, well-known facts. We know that if we have a norm, then we can write the dual norm in this way, and that's going to be helpful. And the other thing we know is that we can swap the order of a min and a max, at least if f has the right sort of saddle function property where we're minimizing with respect to x, we're maximizing with respect to y. These sets are convex, and at least one of them is compact. So those are the only two facts that we're going to need really to try to understand what happens here in nature's problem. So I'm going to show a theorem in a second, and often you sort of bury the details of the proof of the theorem, but it's actually it's pretty simple here, and so I'm going to show it, and it's also kind of, I think it's kind of insightful as to what's going on. Okay, so x is fixed. This is nature's maximization problem. We've already seen that we could rewrite it in exactly this way, where there's a gamma variable which dualized the radius constraint, and then there's this inner maximization where nature is changing the point of support. Okay, so let's use the fact that v corresponds to a two-stage stochastic LP, and let's just plug in for what that means in the dual space. So I've got a max over Xi, I got a max over pi. I can swap the order of those with no problem. So that's what happens here. The pi comes out. There's no Xi here, so the max over Xi came into here. So now I got a max over Xi. I got a min. Okay, I did two things at once, right? I also took the dual here, and I rewrote it using the dual norm, and the dual norm was supposed to be a max, but there's a minus sign, and so there's this min here with respect to z. And there was that gamma, and that got pulled in here. So now we have this maxi min, and this term is it's just bilinear, right? In terms of the Xi and the z, it's a bilinear term, and so it satisfies those conditions. And obviously, the z is over a compact region here, so I can employ this like a Sion minimax theorem to swap the order. And now is when you can really see kind of what's going on here, right? Is there's a max over pi, and there's a max over Xi. So those two decisions are kind of working together to blow this up. When we get to this inner max over Xi, it's unconstrained, right? So it's unconstrained because Xi is in all of our M. And therefore, if pi minus z, if that coefficient is not 0, then this is going to be unbounded. Okay, so that means that we need to pick this gamma out here, and we pay a price for picking that gamma. So that gamma needs to be large enough that this z can exactly cancel out that pi so that nature can't blow this term up. Right, and so it better be the case that this cap pi is actually a compact set. Otherwise, I'm in trouble in terms of that thing possibly blowing up. Okay, so given that we have to pick gamma that large, this term now disappears, and this whole thing collapses to this. And then I'm just saying out here, hey, I need to add a constraint to make sure that I can pick gamma large enough, so it needs to be larger than the norm of the dual norm of the pi for all extreme point solutions here. Okay, so here's kind of the theorem that generalizes that notion. So I haven't said what these assumptions are, but I'll tell you what they are in just a second. So instead of C being all of Rm, instead we could take C to be a convex cone, think like the positive orthant, for example. And this theorem, it's really a negative result. So maybe it should have been like theorem -1, but it says, hey, here's your robust problem. And your robust problem is simply a constant plus the sample average approximation problem. What's the constant? The constant is just this epsilon times the potentially worst case norm, which now is expressed in this more general way. Okay, and those assumptions are that, hey, I've got a feasible and bounded original feasible region, that this pi is non-empty and is a polytope, so it's also bounded, and that I have these points of support, and then I'm using this Wasserstein distance. Right, so why did we want to do DRO? We said, it could be a couple or three reasons. One could be that we're worried about, we want to have a way to model risk. One was that we wanted to be able to kind of integrate the estimation of the distribution, the decision making all at once. Another could be regularization for improved out of sample performance. And this theorem says you don't get any of that, right? It says at least when it comes to making the decision X, just solve the original sample average approximation problem, and that's optimal. Well, if you really are interested in the objective function value, yeah, there's something going on in terms of DRO. But it really is a negative result in terms of the potential benefits of DRO in this case where nature has this unbounded support C. All right, so maybe hang on to these assumptions of feasibility, compactness, ditto for the dual feasible region, and these finite points of support, because we'll come back to that. So so Daniel Kuhn and Grani have a kind of a similar result where instead of just C, the demand sitting on the right hand side, there's a term that involves X there. And under the one norm, they come up with a linear program to solve this. And it's important to note that in this case, it doesn't kind of decouple like I've shown here. You don't get this negative result in general if there's an X that also hits the C. They've also got a result that says, hey, this problem is NP hard in general. And what we're saying here is, that's true if it's NP hard in general when the P is bigger than 1 in the Wasserstein distance. However, it's only NP hard to compute the constant K, right? It's the SAA gives you the right decision. All right, so like if this is kind of a negative result, then well, what do we recommend? And maybe before what we recommend, like the intuition behind what's going on here is really pretty simple, I think. This is the problem that nature is solving when it maximizes over C. If you just think like a news vendor problem or just plot this V function in one dimension, then it's just a piecewise linear function. Nature is getting to move the, say, demand C, and so it can make things worse at that rate if it's making it larger. And it could make the things worse at that rate if it's making it smaller. It has to pay this penalty according to this function to move the points of support. So what are we doing? We're just going to make gamma just large enough so that it exactly cancels out the steeper of those two slopes. And that's all that's kind of going on in terms of this decoupling and canceling things out. Okay, so what are kind of ways around this? In a sense, we've given nature too much power, right? And then we have to be able to exactly cancel that out without getting to avoid getting a trivial problem. That's one thing is, well, put nature in a box and say that nature can only move the demand vector, for instance, within these simple bounds. And then if you take one norm, then no big surprise. You can formulate a mixed integer program to solve this overall problem. And there's a cutting plane algorithm that's embedded. The MIP is basically solving this separation problem here. And there's the cutting plane algorithm is deriving an outer linearization of this cal-v function. So I'm not going to drag you through that kind of logic, but that's very doable. And the price to pay for giving nature this power is solving that MIP. All right, the other thing I want to talk about is let's just say that it is still all of Rm, but instead of using a norm here, let's replace it by a convex quadratic. So take something that looks like a Mahalanobis type distance where, you know, C could just be the identity, or more generally could be some positive definite matrix here to deal with scaling between different types of demand or other right-hand sides. Right, and the kind of the whole intuition of why you might want to do this in terms of the quadratic cost goes back to this picture, where instead of having like an absolute value function here, instead having this quadratic function is eventually penalizing nature more steeply if it moves C too far. And so maybe we won't get this decoupling and we'll get something more interesting if we pursue this quadratic function here. All right, so let's just go back to where we were before in terms of this kind of derivation. We had the cal-v function. Nature was trying to move the demand vector, but it was having to pay a price for moving it away from the nominal point. Okay, that price is now expressed in terms of this quadratic. We can swap the order of the maxes just like we did before. And now when you look at nature's maximization problem over C, it's maximizing. This function is obviously strictly concave. That's just a linear term given the fixed pi. And so this is an unconstrained quadratic with the right sort of polarity that we can just take the gradient, set it equal to 0, and solve for nature's new point of support C. And it was pretty natural what this thing looks like, right? If C, cap C is just the identity, then we know that pi tells us that's the gradient of V with respect to C. So it's just telling, hey, if you move the demand in the direction of the gradient, that's increasing the cost as quickly as possible. And so it's precisely that direction in which nature is going to bump the point of support, and how far it can move. It depends on the gamma tied to the Wasserstein radius. Okay, fine. So now we optimized out this inner C. We're just going to plug it in there. And now we're just going to have the maximization over pi. And so this is a positive theorem that says, let's assume feasibility and compactness of the dual feasible region and the primal feasible region. Let's assume that we have these n existing points of support, the Mahalanobis distance. C is all of Rm. Then this V function reduces to this problem. So normally we would just maximize over pi with this term. But then what shows up here is actually this this non-convex quadratic, right? We're maximizing, gamma is positive, and this is a quadratic term. So we know that we can obtain an optimal solution to this maximization problem over pi at one of the extreme points of cap pi, but in general, I mean, this is an NP-hard problem, right? To solve this, it went from an LP to this non-convex problem. You know, that said, you know, solvers like Gurobi can handle these the bilinear terms that are showing up here, and so I mean, we have a chance to try to compute with this form. Okay, so I'm not going to go into details of what this cutting plane algorithm is, but like this V function, the value function has the original decisions X, but now it has this additional gamma, which is really kind of a first stage decision. So it's making decisions in this space that's have one higher dimension. All right, you've got your first stage cost. You've got the cost associated with dualizing the Wasserstein ball constraint. And now you have this kind of expectation with respect to kind of the nominal distribution, but nature changing the points of support here. And by the way, right, this V function is convex in X. This is a max of a bunch of convex functions. So this cal V function, it's linear in gamma, this cal V function is again a convex function. So a cutting plane algorithm that does an outer linearization of this is viable, provided we can actually solve this second stage problem, maximizing over pi. Okay, so I won't take you into like full detail of what that decomposition algorithm looks like, but I think you can see pretty clearly what it is.
Hi, Professor Morton, there's a question about the previous slide. So the question is how to choose a good C in the quadratic transport formulation.
Right, so if things are, so this cap C, right?
Yeah.
Yeah, so if things are kind of well scaled, and you have you're selling some commodities that all have the same sort of scale, then you could just use the identity for this cap C. However, right, if you have things that are you're selling bananas and you're selling cars, then you might want to rescale things so that when you understand like the distance between 2 points, that they're kind of commensurate. So maybe a better example would be if some of your random parameters affect the reliability of the system, and they're kind of in between 0 and 1 in terms of an availability, but then your other part of your C is has to do with like inflows into reservoirs. Those are going to be really different units, and so you just want to use this C to kind of get commensurate units.
Thank you.
All right, so I just want to kind of give some insight as to what actually happens when you try to solve these problems with an eye towards this goal of kind of regularization, of improving out-of-sample performance. So this is really just like a prototypical problem where I'm going to have some facilities. We're going to install capacity in the facilities. We're going to have demand sites indexed by D. So we're going to build the system, and then in a second stage, we're going to ship widgets from the facilities to the demand sites to satisfy demand. If we don't have enough supply, we're going to have to pay a subcontracting cost. If we overcapacitated the system, then we're going to have to pay a holding cost. And so let me just show the model itself. So there's a minimization of this overall cost with respect to X. Nature is maximizing with respect to P. This value function says what? I installed capacity XG in facility G. Now I'm shipping from the facilities to the demand sites. And if I have leftover stuff, V, then I have to pay the overage holding cost. And if I don't have enough capacity to satisfy the demand, then I'm short. I'm under for customer D, and then I have to pay this shortage cost. So we're trying to install capacity in such a way that we balance these two. All right, so I'm going to show a couple of more plots that look like this, and so let me try to kind of orient you. So here's what we did. These are really not large scale problems, just so that we could try to get some insight as to what's going on. So we just had 10 facilities. We had 30 customers. So little n, remember, is the number of original samples that we had, original observations. So we have 10 30-dimensional demand vectors. Those were drawn from a log normal, and then we forgot the fact that we knew that they were log normal. Okay, well, not quite forgot yet. So then what we did is we took 1,000 out of sample observations, cap in from that log normal. So the x-axis here is epsilon. That's the Wasserstein radius. And then the y-axis is the out of sample performance of that cost. So as a function of epsilon, we get different first stage decisions. Hey, how much capacity did you install in each of those 10 facilities? So there's family of x of epsilons. And then we take those different x of epsilons and we just plug them into no more DRO, just the regular old expectation with respect to 1,000 out of sample. So the question that you're trying to answer in this figure is there overfitting for small values of epsilon of the x to the specific 10 realizations that we saw? And on top of that, so like this is the 90th percentile. The lower line here, hope you can see my cursor, is the 10th percentile. And then this dark line, the solid line, is the mean. So there's a really skewed distribution in the sense that the mean here is bigger than the 90th percentile, in part because of log normal distribution demand, and in part because of the large subcontracting cost that comes from a shortfall. Okay, so this first plot on the left is that the nature can only change the mass, probability mass on the points of support. That's it. It can't move the points of support. And so you can see that for a particular value of epsilon, maybe there's a little bit of improvement in out of sample performance, but this 10th percentile comes up, the 90th percentile comes down, but there's not that much action here. This next plot is the hyperrectangle. So now nature's been put in a box, and you can see that if epsilon gets big enough, then the costs go through the roof, right? Because what's happening is now nature is basically getting to put all the probability mass on a worst case scenario. And then you go test that out of sample, and you really get whacked in terms of the cost because the X is too conservative in a sense. There's like a narrow band where you do get improved out of sample performance. So there's kind of a hint that something good might be going on here. And again, nature is getting to change the points of support here. Okay, so I'm going to go to the next slide, and I'm just going to copy the hyperrectangle over here to the left. And then maybe the more interesting plot is the one with the quadratic optimal transport. So here, the cap C is just the identity. Like all the customers have the same demand for the same kind of widgets, and there's nothing interesting on that cap C. So now what you see is, you might think that we picked a ridiculous problem in the sense that the mean is bigger than the 90th percentile, but actually this is an artifact of the decision we're making. Because if they're for a reasonable value of epsilon, then we're getting an x of epsilon that, number one, performs much better out of sample, and number two, the distribution of that cost function, the cap v, is now seemingly more reasonable in the sense that the mean cost is kind of in the middle between the 10th and 90th percentiles. All right, so this is for log normal demand. And so if our goal was improved out of sample performance, then great. Let's replace it with a uniform demand. And if we do uniform demand, then there's no out of sample improvement. Whether we do the hyperrectangle, this is actually supposed to be the CN, the fixed points of support on the left. This is the hyperrectangle on the right. This is that hyperrectangle again. This is the quadratic transport. So under uniform demand, when we don't have this sort of heavy tail on demand distribution, there's no benefit to doing DRO if your goal is kind of regularization, improved out of sample performance. So what's actually happening to these points of support? What is nature doing? Okay, so the left plot is hyperrectangular support. The gray points are the original points of support. I just took 2 of the 10 or rather 2 of the 30 customers. And we plotted those. And so the gray points here are the original points of support. The green points are what nature did when it has a radius of 1 and a radius of 10. And you can kind of see what's happening is that it looks like maybe that point of support, for instance, got bumped over here. It looks like that point of support got moved over here. It may not be able to put the entire probability mass all the way over here. And not surprisingly, it's got some probability mass at the max demand. If you look at the right-hand set of demand realizations and how nature changes them, then you can see that it's not moving the points of support very much, right? There are 10 original points of support here, and there are 11 total points of support in nature's problem. And you can see that there's going to be some probability mass put here when epsilon is 1, some probability mass put here when epsilon is 10. And so this is behaving in a little bit more smooth, kind of graceful manner, I think. All right, so there's kind of 2 halves to this talk where the halves aren't equal by any stretch. We've done most of what I kind of wanted to talk about in the 2-stage setting. And so like we can handle finite n, and that's just LP, bigger LP, but from an L-shaped cutting plane algorithm perspective, it's not a big computational price. If you want nature to have access to a continuum of realizations, then okay, you need to be careful on how you do this because you may not get any hedging at all. But I think there's an argument for using this quadratic instead of a norm-based penalty. But there is a computational price. We have to solve that non-convex quadratic LP for a subproblem. There's not always an out-of-sample benefit, of course, but there can be benefit when the distribution of this cost function is skewed. And the kind of ideas I talked about, it's not just for this setting. I mean, there are other distance measures, maybe with distance in quotes, and sometimes where phi divergence or otherwise. Okay, so that's the 2-stage setting. And so let me just say briefly a little bit about multi-stage. Like how well do these ideas really carry over to multi-stage? And so now what we do is we kind of have a value function that's defined recursively here in a T-stage stochastic LP. And kind of the setup here is what? That we have to be feasible when we get to a particular stage. And to think about a concrete example, like the hydroelectric scheduling is one pervasively used setup here, where every month we decide how much to release from a reservoir, how much to hold in the inventory of reservoirs, and the reservoirs are connected by kind of network flow style constraints. We either have interstage independence, or we have, for example, an autoregressive style dependency on what the inflow vectors might be. And the usual setup to make this tractable is that you might have like 30 realizations of inflows at any particular stage, but you might have a large number of stages. So for example, in Brazil, they'll solve monthly models for 10 years, so 120 stages with 30 realizations of inflows at each of the stages. You know, what is a solution here? Before we had this kind of X of epsilon, and here the solution is really a policy, right? You've got these 30 realizations, the inflows were low, medium, or high. We made some decision on how much water to hold in the reservoirs, how much to generate with hydro energy now, and then we have to keep making that same decision over and over again, and the solution is really a policy. You know, so I said that you can handle 30 realizations a stage and you can have 120 stages. That doesn't look all that viable when you draw trees that look like this, but this stochastic dual dynamic programming algorithm, what it really does is it says, if I really have interstage independence, then I don't need a different value function at each one of these points in the node, how much water I have in my reservoirs, of course, depends on whether it's been really dry or really wet. But I only need one value function. So I can just have the piecewise linear approximation, the outer linearization at each stage. And you can actually compute a lower bound here in the sense that you take the 30 descendants of a particular node, and if that truly is the population mean, then you can compute an exact cut. So when we go to a DRO setting here, what's going to happen is there's going to be sort of this rectangular assumption is going to be in place where we make a decision. After we make that decision, nature is going to choose the probability mass on those 30 realizations. Then we're going to make another decision, and then nature is again going to choose a probability mass on those 30 decisions. And actually a different one over here, right? So nature is going to have a separable problem where it gets to put probability mass here, but chooses a different probability mass conditional on being at this node. And so that kind of formulation is written here, where now we have like a ZW star for Wasserstein. And then we have this nested min. Nature picks a worst case probability distribution. We pick another decision X, nature picks another probability mass function, and the thing just rolls forward in this way. So there's a lot of details that I'm not going to go through here. I just want to give you a little bit of flavor in terms of the same kind of results that we saw before. And I want to be clear that here, we're not changing the points of support. We just take the existing points of support. So here there's a problem with 10 reservoirs, 12 total stages, and then we're either going to have like 5, 10, or 30 scenarios branching out of each stage. And then we're going to do the same sort of thing with out-of-sample testing with 1,000 total paths through this tree. So you might, well, 5 scenarios seems really small, but this is really 5 to the, I guess, 11. Or 10 to the power 11. So, I mean, when you look at the overall tree, there are a substantial number of scenarios. Okay, so this is when there's just 5 scenarios branching out of each tree, out of each node in the scenario tree. And you can kind of see 10th and 90th percentiles, 20th and 80th percentiles, a mean and a mean. And it's the same thing. Now we have a policy that's parameterized by the Wasserstein radius. So this is when there's 5 and you can get some improved out-of-sample performance using the DRO approach. This is when you instead have 10, so 10 to the power 11 total leaf nodes in the tree. This is just copying over that previous, and now we have 30 at each branch. And so it's the kind of thing where if you've got enough data, then you don't risk overfitting here. You don't get the regularization benefit unless you're overfitting to a smaller kind of data set. The other thing you can do is, like the origins and the destinations, there's something in between giving nature a continuum or having 10 origins and 10 destinations, right? You could have 10 nominal scenarios, but you could have 30 scenarios selected in some way as the destination scenarios. And that's kind of what's going on in this picture where you see, hey, if things can get bad in terms of nature putting probability mass on a worst case scenario, but that's what the 10 to 30 means, 10 origin and 30 destination scenarios in Wasserstein. All right, so I think this is the last slide. And I know the multi-stage stuff was quite fast, but I wanted to give you a sense that this is not just, we're not just stuck in a 2-stage setting here, that we really can do time dynamic problems. So we handled the discrete Wasserstein as opposed to the continuous Wasserstein. It's also possible to do phi divergence type stuff in this setting in a pretty clean way as well. So continuous Wasserstein is a little bit trickier here. There's some modeling issues that rectangularity gets you into a little bit of trouble with. You can have an extreme realization that nature can pick, and you can do that quadratic story just like from the 2-stage. The problem is due to rectangularity, it doesn't necessarily, or just in the simplest implementation, it doesn't propagate forward in a simple way. The fact that you had a drier scenario than usual doesn't, it's hard to propagate that in a multi-stage way. I mean, another thing I don't know how to do is this. Suppose that you say, okay, my nominal distribution is interstage independent. And I told you that nature gets to choose a different probability mass function at that node and at this other node at the same level in the scenario tree, kind of due to rectangularity and separation. I don't know how to tell nature, hey, the probability mass that you come up with, it has to satisfy interstage independence. Because now you're coupling problems in a difficult way in terms of the max. And I didn't really mention this, but lower bounds are easy to calculate here. But actually upper bounds in the multi-stage setting are hard. So that's kind of all I wanted to cover. And so I'll go ahead and stop sharing there, and happy to try to answer any questions.
Thank you, Professor Morton, for the great talk. So the first question is, it seems that you have a constraint, the linear constraint, which is about the system model. I was wondering whether it's possible to also incorporate a model misspecification.
Yeah, so, right, so I don't know whether we could do that in a clean way. Right, so here, yeah, so basically, like if I have an epsilon of 0, then right, my only feasible solution for nature is to put all the probability mass there. And so I guess you can do the following, right? You could have the situation where you generate in a testing environment. You could have a situation where you generate data from a true model, but then you misspecify the model in your Wasserstein setup, and then you try to understand the question. I ignored this factor from the model, and how well does Wasserstein really do in covering that model misspecification? So yeah, I mean, it would be interesting to look at exactly that, but it's not something that we've tried to formalize in the math here.
Thank you. And another question is, it seems you focus on the Wasserstein, the ambiguity set defined using Wasserstein distance. I was wondering whether it's possible to use other Wasserstein distance, say second order Wasserstein distance, or other divergences like chi-square or KL divergences. Yeah.
So absolutely. I mean that is relatively straightforward to push through. Especially the latter part is clear, right? So like if I have a chi-squared type distance, then I'm going to end up with an SOCP instead of the LP in the setting there. But that kind of can go through in a clean way. Same thing if you want to do like KL divergence, then that, you know, there's an entropic function that's going to show up in a natural way when you take the dual there, and that can go through in a clean way as well. And I think, yeah, at the price of a nonlinearity, right? You can handle. So I guess we did the case where we have like a p equals 2 in the Wasserstein, right? We kind of went from a Wasserstein norm-based distance with an overall p is 1 to a quadratic, and we didn't need to take the square on the outside, right? We just squared kind of both sides in that formulation. So yeah, those things are quite viable, I think.
Thank you. And so another question is what if the noise has Habit-Hill distribution? So will that have an effect on the algorithm or the theoretical guarantees?
No, so I think in terms of the computational tractability, that's that's fine even if we have heavy tails here. And in fact, I mean, I think that's kind of the setting where there's kind of larger potential benefit. So.
Thank you. And it seems for the two-stage case, you commented that the similar technique can be used for risk-averse learning. And but do you have similar result for multi-stage case?
Yeah. So yes. I mean, there are results that say. So the issues that come up in the multi-stage setting include the fact of the notion of like time consistency in terms of decisions that you make, right? So kind of the natural way to formulate things or at least one natural way to formulate things to ensure time consistency is to do the kind of nesting in the way that I think I kind of tried to show in terms of alternating the min max at each stage. So like a simple example there is nested C-var. So you can have a weighted sum of expectation and C-var, and then you embed that in kind of a nested way where you take that result and then that becomes part of the C-var tail. And you have to be careful there in terms of formulating things, right? So like if you're really looking at something like a 5% tail, and then you take the 5% tail of the 5% tail of the 5% tail, then things don't work out the way you really want them to. So you kind of have to balance the weight that you put on the C-var term with the tail that you're looking at, so that ratio is pretty much 1. Otherwise, it becomes meaningless or it blows up to the worst case in the nested setting. But I mean, the overall story is that you can do this with entropic, you can do this with nested C-var, just as kind of examples.
Thank you. Thank you. That's all the questions I have. Thank you again for your time.
But great to get to talk to y'all. Thank you so much.
Thank you. Also, we would like to thank the audience for coming today and look forward to seeing you next week. Thank you. Thank you again.
Thank you.
Bye.